All right, and we're back. So today is day 15 of Coding Every Day. So it's January 30th, 2025 at 3:06 p.m. And today is a Thursday. So I'm supposed to have a class later today, but it was canceled. So hopefully I can get some homework done. Okay, so we're back with tree problems today. I haven't looked at this problem at all. Yeah, so let's get into it. So binary tree level order traversal. Given a binary tree, return the level order traversal of it as a nested list, where each sublist contains the values of nodes at a particular level in the tree from left to right. Okay. So it seems like understanding what this problem is asking is good. I can do it in O of n, I think. All right. I think you just do a breadth first search. I think you just do a breadth first search, and then after every layer, you create a new list and append the old one. So let's try that. And that's O of n. So we're going to have our Q here. All right. And then we're going to make it equal to root. So it just has root. Then we're going to say while Q. And I believe I can do an end space. So then we'll also have visited, which is a set. And we want to have our results list. Okay, so while Q, we'll say current equals Q dot pop. For child in current. Oh wait. I think we can say that. So basically for each child, we want to say if child, if child and child not in visited. So if it's not null, I'll also just say up here if not root, we'll just return an empty set for the edge case, this one. Okay, so in this case, so after we explore both the children, well, first of all, what we want to do is Q dot append left child. And we want to, after we explore a node, we want to say visited dot add current. And we want to, so we could have like, what do they call it? Level? Yeah, level. So, okay. So we don't want to do it with just a child. So we want, okay, so that's sort of the hard part. For now, I'll just make every level like unique to the child. So in this case, it would give us 2 by itself, 3 by itself. Or wait, no, it would give us 1 by itself. All right, let me think about this. me zoom in. Okay, so our Q is over here, and it just equals, so if I have 1, 2, 3, our Q starts as 1. We pop it, and then for every child, we want to, if it exists as a node, then we add it to the queue. So now the queue would instead be 3, 2, like this. And then also we say, so after that we want this to be invisited. Well, I don't think we actually need even a visited set because it's a binary tree. So by definition, there will be no loops. So if I just print current, I want to see what that does. And what do we have to return? A list of lists. So I'll just return an empty list for now. And I just want to return outside a function. That's my bad. That's my bad. We don't need visited. And I also probably want the value so it's readable. And we get 1, 2, 3, 4, 5, 6, 7. Okay, perfect. So now it's just a matter of categorizing them into different levels. So a way I'm thinking about it is you could just have a count. So for instance, this would be 1. And then you check after you're done with this if it equals 2 to the power level that you're on. So we're on level 0. So because this count equals 2 to the power 0, then we append this to our final answer. And then, so then level goes up by 1. So now it's 2 power 1. And count goes back to 0. So here, after we're done with this one, it's 1. 1 does not equal 2 to the power 1, so we keep going. Then here it's 2. And now this equals 2 equals 2 power level, so then we add that. So I'll try that. So we'll have a variable called counts, which I will set to 0. And we'll have a variable called level count, which I will also set to 0. So after we're done, so every time we do this, every time we pop something, I'm going to say count plus equals 1. And then if count equals 2 to the power of the level that we're on, then we add level, so results dot append. So this would be level count dot append level, and then we set count to 0 and level plus equals 1. So now we'd be at level 1, count goes to 0. So now we just need to add, so I think what we want to say is level dot append current, like that. And also we need to reset level, like that. Okay, so let me just print out res here and see if I have any errors. Count goes up by 1 every time. If it equals the level count, then we append it and reset it. Level, it's not associated with a value. That's fair. Level counts plus equals 1. So it is 1, 2, 1, 2, 3, 4. Okay, let me just try returning it. See what that does here. Am I supposed to append the values, perhaps? Like that? Okay, so that seems to be working. That seems to be working. My output is a list of lists, but it's expecting just one list. Okay, let's see if there's any edge cases. 1, 2. 1, 2. So if we consider this case, 1, 2, like this. Oh, I guess if we run out of... So if it's not a fully complete binary tree, then we want to add the remaining... So I guess here I could just say res.append level afterwards. I should add it as a test case. Oh, that doesn't work. If level, like if it has anything in it, then just add it. All right, let me see if that worked. It did not. Okay, we got past the other test case, so that's fine. All right. So here we have yeah. Okay, so the nulls are messing it up a little bit. So in this example, we have 1, 2, nothing, 3, nothing, 4. Wait. Hold on. 1, 2, nothing. 3, nothing. 4, nothing. Okay, so in this case, if we trace our code, I'm guessing it's not updating count when it's null. So our queue starts at 1, and then we pop queue, and that's currents, and then we append level is just 1 right now. And then for each child, so this gets appended, like 2 gets appended here, actually into the queue. And then this doesn't do anything, and then count goes up by 1. So we explored 1 node, so that seems good. I think the problem now is, so this is true as well, right? Because 2 to the 0, so we're going to reset everything. That's good. So now current is 2. So this resets. So so level is going to append 2. So I'm guessing it probably does 2 and 3 on the same level. Let me see if that's what we do. Yes. Okay. So we have to basically increment count by 1 if it's null. So let me try this. So we'll say count plus equals 1 and continue. So now count will be added more. So now we have everything on its own level. That's because the level count never gets updated. Okay, so what we want to happen is, so count is here, and then maybe what we could do actually is append nothing, right? So append the nulls actually, and then if it's null, so if current, if not current, so if it's null, then we'll say count plus equals 1. Or maybe just do all of that if it's not current. Oh, my output was that. Oh. So either way, I'm thinking, sorry, if current. So if it is not null, then do this again. If it is null, we'll still count and check this. Okay, so now we have, now it's just, okay, we're further from the truth now. So we output just 1. Okay, I'm going to go back to what I had. Actually, I'm going to stay with that because it makes sense to me. Because we want, okay, so for instance, 1, that's good. And let me just make sure it was like that. Okay, so 1 is good. We append 1 to the level, and then, oh, if not child. We don't want if not child. We want, I think we just don't even care if it's, with this approach, right, we don't actually care if it's a child or not. And then let's just make sure we're not appending any empty levels. Okay. So we're back to where we were. So let's see. So now I'm outputting 1, 2, 3, 4 together. Oh, is it because now these don't have nulls as well? So I'm thinking you can like increment count as a function of what level you're currently on. So if we are on level 1 and we encounter a null. Oh yeah, this is a little tricky because we have this. Okay, so for instance, if we're on level 1 here and we encounter a null, then that gets rid of all of these possibilities down here. So it's not necessarily 2 to the n anymore. Maybe instead of using this, what you can do is, so let's try to define when we know that we've moved down a level. So so in the case of this, right, you can just count, basically, is all I'm doing. So, okay, my count's at 1, and that equals 2 to the 0. And then I go boom, boom. Count's at 2, and that equals 2 to the 1. And then reset count, 1, 2, 3, 4. And now it's 2 to the 2. Obviously, the problem with that is if you have a tree that looks like this, it's going to group these two together, even though these should be in separate groups. Okay, so let's consider another tree where it's partially complete, maybe something like this. So maybe for every tree, it could be the roots, and also we can have a tuple of its height. So we know that root 0, for instance, all the children of root 0 will be root 1. So this will be 0. And then when we add it to the cube, we'll add whatever I am plus 1. So that way we have this sort of architecture here. And then maybe what I could do is put these in a dictionary and just add it to the corresponding dictionary. This should be 2. Okay, so let's try this. So now instead we're going to have a list of tuples. So it'll be root 0. And then when we add it, we're going to add so current is equal to q dot pop. So we're going to have, okay, so let's we're pivoting the whole architecture here. All right, so currents is q dot pop. So we want this to be root. So current node, I'll just say node and level. Okay, so if and then maybe we could go back to just not adding nulls. So we can say, we can get rid of that. So for child in, then we'll copy that. So node dot left, node dot right. So for both of the children, or for both of the children of this node, we will say if it's not null, then we will q dot append left. Now we want to add node, or we want to add child and also level plus 1. Level plus 1. So now what this will do is it'll add the correct level. And maybe we can have results. Okay, so we don't need this stuff anymore, I'm pretty sure. So after we're done with that, can I make like a default array or something like that? Let's see what my parameters are. It's less than 1,000. So that means there has to be, well, the number of nodes in both trees. All right, let me just put it in a dictionary for now. And then maybe I could figure out how to translate it. Okay, so the idea is we want to say, so after we're done searching as children, we want to add to dictionary. So we're going to say if heights not in dictionary, then say d of heights equals empty list. And then we want to say d of heights dot append node. So essentially we're going to have our data structure is integers. And then at that height, it'll be a list of all the nodes that are in it. Okay, so if I print D and return that. And we should also probably append the node.value. And it should be level instead of height. One argument, we need to make it into a tuple. Okay, perfect. Perfect. Okay, so now thinking what I could do is just say like result equals a list that is the size of the dictionary. I don't know, can you say, can you do that? Can we convert a dictionary to a list? Probably not, right? All right, so let's think. So I want to translate. So I have keys like this. I guess I could say, oops, sorry about that. D.key. So if I print D.keys, that will give me the levels, right? Looking at 26 minutes here. Okay, so yes. So let me say result equals empty list times length of D. And then I can say for L and D.keys, results of L equals D of L. So in other words, so this will be a list that has this many slots in it. And then we're going to say for L, so for instance 0, result at index 0 equals that list. So let me try printing result here. I'm not printing anything. List index out of range. Okay, so let me just print L here, see why that was incorrect. 0, 1, 2. Yeah, so it has all those indices. Is it still incorrect? So is it if I do an empty list, is that the problem? I guess I have to populate it somehow. Okay, so hopefully it replaces the 0 with a list. Yeah, so the spacing's a little bit different, so hopefully that doesn't matter. So let's return res. Hopefully that works and the spacing doesn't. Okay. Okay, sweet. Great. This was a great problem. I enjoyed that one. I think I did it in the recommended complexity as well. O of n time, so n is the number of nodes. Yep, so we go through every node exactly once. Well, it is a breadth first search. So for every node, it's like for every node we do two things basically. So yeah, it's n still. And then appending left is constant. This is constant. This is constant. This is n. Well, this is h. And then this is h. Not sure if there's a better way to do this. I just thought this was the most intuitive way, where you kind of just use the level as the index. Because I could do it beforehand, but the problem is you don't know how many heights there are until after you do these calculations. So convert dictionary to nested list, basically. That's all that does. And then I can delete all of that. Yeah, that was nice. So I found a good way to the problem. I think if I take this out, it probably fails, right? Oh, it still passes? No, okay. Oh, I don't mind having that there. Okay. Yeah, great problem. Basically just a refresher on breadth first search. And the trick that I needed was that, so for each element in the queue, you also want to have its level, instead of doing the math thing, because it didn't hold up against this tree here. Which one is it? This one doesn't hold up against that because the nulls kind of mess things up, but this way it works in every case. So something to keep in mind. You can also store its level. So yeah, all right, everyone. Thanks for watching. Happy about this one, and I'll see you guys tomorrow.